So we're down to the final two lessons, and the last two lessons are quite short. So I'm going to do wheel and axle and gears first. That's the longest one. And then the second one's only about 6 slides, and it's the easiest simple machine to do. So this will finish off simple machines and finish off math for the year. So first about wheel and axle. I mean, we're pretty familiar with wheel and axles and gears to make things easier to move. But I want to just kind of talk a little tiny bit about why they work the way they do, rather than just saying it works. I know it works because I've used wheels to make things move easier. I mean, imagine a car trying to drag a car with wheels stuck. I remember at one point having an axle snap on a car. Talk about a very difficult car to push off the road. We managed to get it off the road until somebody came to tow it, but it was very, very hard to push. Some kind people stopped. So wheels and axles, we know they make things easier to move. We know gears are really important to vehicles. So I just want to talk a little bit about how force and friction and a little bit of the physics comes into play, just a really brief introduction, and then we'll do a couple of gear ratio calculations. So what's the purpose of a wheel and axle? Well, I mean, the purpose is pretty obvious to us, to make it easier to move things. So wheel and axle can either change the force of an object, we can use it to change the speed of an object, or we can use it to reduce friction. The biggest purpose for using a wheel and axle, there's two of them. Usually we're reducing friction and often changing force, but it's really hard to say which of those three is the most important. But reducing friction is the biggest reason for using wheels. It's much easier to roll something than to slide something. And that's because the friction sliding an object is always higher than the friction for rolling. So what is a wheel? A wheel is just like a lever. It's like a lever. You can see in this picture, it's like a lever. The axle is your pivot point. So you put a force on the outside edge of your axle. It pivots around the center of the axle, and then the wheel's attached on the outside edge. Now, for these calculations, you're always going to want to stop and think, where is my effort? Is the effort my input force? Is it on the outside of the wheel like a steering wheel? Probably shouldn't have said that right now. Or is it actually on the axle? So we kind of have to think about and analyze a little tiny bit. And we'll think about, there's advantages to both of them, but they change whether the mechanical advantage, whether it increases my force or decreases my force. So first question, where is the force? I think I gave you the answer for the first one already. So we have somebody and they're steering a car. Well, their hands are on the outside of the wheel. It's turning your steering column, which means the force or the effort must be on the wheel and our load or our resistance is on the axle. I'm using the outside of the wheel to move that steering column. Well, why would I do that? Well, we're going to find, if we just think about torque, let's just think about what we know about torque, because we talked a little bit about torque earlier. If I apply a force a long distance from the steering column, as opposed to applying a force close to the steering column, I can use a smaller force here to generate a larger turning force, a larger turning torque, than if I put my force just on the steering column. Just as a practical example, if any of you guys are into old cars, I'm not really a car fanatic. I'll tell you that right off. But one thing I've noticed, and it's funny because you notice things because of what you teach. One thing I've noticed, I guess it was 2 years ago, we had the classic cars in Summerside, or did the car shows. And looking at the cars, a lot of the old cars had very large steering wheels. Often they were much larger than the steering wheels we have. And what that was is that there wasn't power steering. So it took a lot of force to turn the wheel. So what they did, they make the wheel a little bit bigger so that it's easier to turn. Turn off my phone here so my emails don't keep coming in. Okay, so there's a practical example. The bigger the steering wheel, the easier it is to turn, although perhaps the tighter the seat space. Now, let's think about the wheel that you're driving on. This is typically when we think of wheels in a car, we always think about tires. So, well, where's the force? Where is the effort and where is the load? Well, if we think about a vehicle, what drives, does the tire drive the car or does the car drive the tire? Well, that's an obvious question. The effort is applied to the axle because your engine is connected to the axle. And it causes the wheel to turn, and the wheel is our load source. So the effort is applied to the axle, which turns the wheel. Okay, in this case, we use a small amount of, the reason for, we're going to find we get a different mechanical advantage here, mechanical advantage of less than one, we're going to get a mechanical advantage of greater than one here, but we're going to find that what's the advantage? We have a force applied to a very small wheel and it's distributed out over a larger distance here. So that's going to make us so we can travel further with the same rotation. Okay, so just thinking about where's the effort. Now, how do we calculate mechanical advantage for a wheel and axle? It's very easy. There's two ways. First method is using force, exactly the same as we've done before. You have your force where the load is applied divided by the force where the effort's applied. So if my force is multiplied, my mechanical advantage will be larger than 1. Let's look at the next one. Ideal mechanical advantage is calculated using a radius. Why would we use radius? Well, you notice with levers we use distance, but we use radius when we're looking at, I'm just going to go back here, we use radius when we're looking at a wheel and axle because the distance is equal to either the radius of the axle or the radius of the wheel. Okay, so we'll just use radius. You could also say instead of radius, you could put diameter, although you know how to switch from radius to diameter anyway. So easy, simple formulas, and I just make a note of the formulas and then you'll have them for going through on your test. But the formulas, you'll notice a lot of them they're very much the same. So let's do a couple wheel and axle math questions. First of all, and my picture, something's gotten misaligned here. So our 200, this pivot should really be in the middle of the wheel. So you'll have to pardon the little adjustment that's happened there. Using force, determine the mechanical advantage, or what is the mechanical advantage if the axle is driving the wheel? I've got some extra words in there. That happens every now and then. I think I've recorded this 4 or 5 times and scrapped it every time because I'd get 3/4 of the way through and I'd go, oh, darn, I should have changed that. So this time it's a final take. So how do we find mechanical advantage? Well, if we went back to our last slide, if you have it printed off, you have it there. Mechanical advantage is equal to the force on the load divided by the force of the effort. So this says the axle is driving the wheel. So in this case, this would be like the axle driving your car wheel. Well, what's the mechanical advantage? It's easy to calculate. The force on the load, so it's driving the wheel. So this is my load here. The axle is where the effort is, so it's there. So we're going to have 70 divided by 200, which gives us a mechanical advantage of 0.35. You'll notice if the axle drives the wheel, the mechanical advantage is always less than 1. That's because you apply a large force close to the axle over a shorter distance and a smaller force over a larger distance. What's the advantage? Well, the advantage is for every turn of the wheel, I move a longer distance. So even though my force isn't increased, we're going to find we move further, and because we're moving further, that's technically an advantage. It's just not a force advantage. So we find our mechanical advantage is always the force advantage. So there's not a force advantage, the force is reduced, but there's still a good reason for using that, and it's because it would increase distance. All right, let's use distance to find the mechanical advantage. So if we use force, we get the mechanical advantage if we include friction. If we use distance to find mechanical advantage, it's what the ideal mechanical advantage would be because the distance isn't going to change whether there's friction or not. The axle is going to be in the same location, the wheel is going to be the same diameter, even if there's friction. So this is really our ideal mechanical advantage. How do we find that? Well, if you look at your formula, with force, loads on the top and efforts on the bottom, but with distance, we're going to have the radius of the effort on top and we have the radius of the load on the bottom. Thus, we should have the same kind of mechanical advantage. All right, so what do we put in? Well, our effort is here. So we have a 6-inch wheel and we can, as long as we both, the units would cancel out. So your radiuses or your distances always are in the same units. We don't have to switch them to anything. And then we get 20 on the other side. This is my load distance because the load is the wheel. So 6 divided by 20 gives us a mechanical advantage of 0.3. Now, the next question on this slide asks you to stop and think. If efficiency is always smaller than 1, so machines can never be 120% efficient. There's no bonus points in machines. So is it possible that the axle could be driving this wheel given those numbers? Well, let's look. If the efficiency, so efficiency goes back to our first lesson. It's equal to our actual mechanical advantage divided by ideal times 100. Or if it's less than 1, we would say just, I'll take out the times 100. We just leave it as a ratio, okay? So it has to be 1, or if it's, or 100%, so okay. So let's figure out what is the mechanical advantage, because this is going to tell us, is it possible? Well, the actual mechanical advantage is 0.35. So my force is 35 hundredths bigger, which is actually makes the force smaller. It's kind of a weird way to say it. Divided by 0.3, what do you notice? Well, if you divide these two, you're going to get, let me plug them in. 0.35 divided by 0.3, we get 1.17, or 117% efficient. So let's read the question again. Is it possible that the axle is driving the wheel? Can you have 117% efficiency? Nope. Ideal mechanical advantage can never, ever, ever be bigger than the actual mechanical advantage. It's not going to happen ever. Okay, so that's one of those little things. It's just a really good kind of think question. What happens? All right, same wheel, but we're going to flip the question. And we're going to say, well, this time, let's use force to find the mechanical advantage of the wheel. And what is it if the wheel drives the axle? So the wheel is my effort and the axle is my load. So now we're just going to take our numbers and we're going to flip their positions. So my axle is the load, like a steering wheel, where the load is on the steering column. That's what I'm turning. And my effort is on the outside edge of the wheel. So this is a very good, steering wheel is an excellent example for this one, and it kind of looks like a steering wheel if you stop and think about it. So let's calculate our forces, same as before. So we're just using the same ratios. The actual mechanical advantage is equal to the force of the load divided by the force of the effort. Load happens to be equal to 200 pounds. My effort is 70 pounds. And we can just use pounds. That's okay, as long as you're measuring. If you can do force in either newtons. When we do it in the context of simple machines, we're allowed to put force in pounds as long as the force is in pounds for both effort and load. Okay, so 200 divided by 70 gives me 2.9. So my force, the amount of force I can put on the column, was multiplied 2.9 times by using the wheel. All right, next it says determine, using distance to determine mechanical advantage. What is the mechanical advantage if the wheel drives the axle? So we're going to use distance this time. So this is our ideal mechanical advantage. Is there friction involved with your steering wheel? Definitely friction involved. You've got lots of moving parts. Anytime two parts rub together, you're going to have friction. So ideal mechanical advantage is going to use distance. And remember from before, the position of the load and the effort switch places. So we're going to have the radius of the effort force divided by the radius of the load force. And what is our mechanical advantage? Well, our load is on the axle. So that's going to go on the bottom. And our effort went on the outside, this 20-inch wheel. And we can use our distances as either, you can use it with diameter and diameter, because if we divide both both the top and the bottom by 2, it's just going to make an equal fraction. So you can use diameter or you can use radius. Maybe I will actually adjust that just for the sake of anybody that might get confused. Let's figure out or plug the radius in. I know sometimes I've been told that when I switch things, even though I say it, it doesn't always make sense. So this would be our radius is 3 and the radius is 10. Okay, so just so you have that, but you could use either radius or diameter. 10 divided by 3 gives me 3.3. Now I want to ask you the same question that we had on the other slide. I didn't have it typed in here. Is it possible? Is this a possible formula, a possible setup? Or do these forces and distances work if the wheel drives the axle? The answer to that is this is possible. Why? Well, the actual mechanical advantage is less than ideal. So we know ideal conditions never exist. So the actual always has to be lower. And in this case, the actual condition is a little bit less than ideal, which means this is a possible scenario. You can never be better than the ideal. The ideal would be to get like 100% in your course. And we know that we can never get more than 100% now. Occasionally, there might be a way to get enough bonus points, but at the end of the day, your transcript is still only going to say you got up to the ideal mark. You can never get above that ideal mark. So think of that when you think about mechanical advantage. So that covers our wheels. Now we're going to look at gears. Gears are just 2 wheels stuck together. If you think about it, we've got wheels with teeth, a lot of the same type of scenarios, but because they're not stuck on top of each other and they're put separate, things change a little for the math. So with a wheel and axle, they turn together. Okay, so if we look at our wheel, for every 1 turn the big wheel makes, the little axle, which is attached to it, makes 1 turn as well. So we notice these wheels don't change speed, but they do change how far I travel each turn. In the case of a steering wheel, it's actually it's good that the steering wheel is large because I can make a big movement, but it only affects a small movement on the steering column. It's a smaller angle, which is good. We don't want massive movements, or driving would be jerkier than it might already be. So when we look at gears though, because they're side by side and they mesh together, for every 1 turn that this little gear makes, it's only going to move the big gear the same number of teeth. So we're going to get speed changes that happen here. And we've talked about that already. So with this type of scenario, the biggest reason for using them, yes, we're going to reduce force. Yes, we're going to change speeds. We'll change force, we'll change speed. Reducing friction, yeah, we'll reduce some friction, but that's maybe not the primary purpose. All right. Now, again, just like wheel and axle, you have to know whether gear A or gear B is applying the effort and which one's the resistance or the load. So first of all, just a couple things to talk about with gears. No math involved here, just, I guess it's direction of turn is technically math, clockwise, counterclockwise. You can argue that's math, but no calculations. So if you have 2 gears meshed together, what's one of the important things that happens? Well, these 2 gears are exactly the same size. When gears are the same size, they don't give you any mechanical advantage. So what do? Well, you'll see here, it says no idler opposite direction. We'll talk about the idler over here. If you just have 2 gears together, the gears turn in opposite directions. So even though the gears don't change force and they don't change speed, because they change direction, there's a reason to use it. So sometimes we're not interested in the mechanical advantage. Sometimes we just want to keep everything the same, the force is the same, and just change direction. So that's one reason for using gears. This question, mechanical advantage of one can be useful in changing directions, all that's needed. You might see that again. I'm just putting a little star beside it because if you're looking, that might be something to jot down because that might be a question that shows up. Just maybe. All right. What if we put a gear in the middle? What happens? This is called what we call an idler gear. Okay. So this gear, you'll see these two gears are the same size. Because they're the same size, they don't have a difference in their mechanical advantage. This little gear in the middle, what happens? Well, you'll notice if you went from the big gear to the little gear, you're going to have a change in mechanical advantage. But if these two are the same size, if you go from the little gear to the big gear, it's just going to change back up. So in this case, we don't have any mechanical advantage in terms of force because these two gears are the same size. This idler gear just helps us change direction. So this one doesn't change the mechanical advantage. So the only thing we need to worry about is the driving gear and the driven gear. And as long as they're in a long sequence, we don't have to worry about what the gears are in the middle. They kind of all cancel each other out. There is a math way to show that, but I really think that's maybe more than what we need. Now, if we stack two gears together on the same column, on the same axle, then we would have to consider some compound gear calculations. We're not really going to get into that. I will give you just maybe 3 or 4 slides that talk about what if you put two machines together, what happens. Okay, and it's just really, really simple, just so that you know what concepts occurring. All right, so an idler gear just changes direction. So you'll see now the driving gear and the driven gear both turn clockwise. So normally gears turn in opposite directions. If we want them to change turn in the same direction, we have to put a little gear in the middle. It could be a little gear or a big gear, whichever. A gear in the middle that would cause the driving gear and the driven gear to turn in the same direction. The other way we could get two things to turn in the same direction would be to use a belt and pulley. And we'll look at that at the very end of this lesson, just very quickly. So gears and torque. We know that gears change torque. I know you talk about that with cars on a regular basis. Now, this is one of those pieces that I had to do some learning on because I wasn't as familiar with it, but it's really pretty logical. And over the years, I think I get better at explaining it, but you can let me know what you think. So the first thing I want you to think about is why does a small gear have less torque than a big gear? Well, let's look at our picture. Now, Newton's third law. Remember Newton's laws from the last section? It says that if this tooth pushes on this tooth, the other tooth they push back up, equal and opposite. Well, Newton's laws state that. So that means this force, the force applied to the teeth has to be the same for the little gear and the big gear. So let's look at our torque formula. The formula, I've got extra notes in here. So that's Newton's third law, equal and opposite forces on the teeth. Now, the torque formula is torque equals force times distance. We learned that with levers. The longer the lever, the more torque at the center. So we have a different distance to the center of each wheel. So the force stays the same. We said the force on the teeth of the big gear and the little gear is identical because of Newton's third law. So if the large gear has a longer distance, so I'll say torque equals force times distance. If the distance increases, then it must have more torque. If we have a little gear, torque equals force times distance. The distance is smaller, so it must have a smaller torque value. Well, why do we even care? Well, I do have a quote. I don't want to jump the gun because if you give me about 3 slides, I'm going to ask you about this again, but we'll give it to you now. Torque is the turning force. So let's say you're driving up a hill. Are you going to want to have the gear that's connected to your axle? I know it's not a straight connection, but the gear that's driving your axle, if you're going up a hill and you're trying to get up that hill, you need more turning force because a hill is harder to climb. Would you want to have more torque or less torque? Well, you're going to want more torque. It's one of the reasons why we gear down. When we gear down, that means we're using larger gears to drive the car. They're not going to move as fast, and we're going to see that when we go forward. but they provide more turning force, which makes it easier to climb. So really, really, really simple. If you think about that gearing down, gearing up, when I want to go faster, I don't know, hopefully some of you guys or most of you have maybe driven stick shift at some point, but if you've driven a standard, you notice you gear down if you're trying to go up a hill and you need a little extra push. And when you want to gain extra speed out on the highway, I had a 6-speed, you'd go up to your highest gear. And that's because in that case, you were having a smaller gear that was driving the axle. So it had less torque, it had less push, but it would turn faster. Hopefully that makes sense to you. If it doesn't, we'll see. We're gonna see that in a second. So how do we find mechanical advantage for gears? Well, there's 3 formulas we can use, and we're going to use all 3. The first formula says the torque of the driver gear divided by the torque of the driven gear. So you'll notice instead of using force, we use torque. Why? Gears are used to turn things, so we more often use the turning force. We could have done torque for our other wheels as well, for the other wheel and axle as well. We would have to adjust the position of the driver and the driven to make that work. All right, we can also find out gear ratio using speed, mechanical advantage using speed. Mechanical advantage is just like a gear ratio, except it's not the ideal gear ratio. And then for ideal mechanical advantage, we count the number of teeth, and it's the ratio of the teeth of the gear that's driving the driven gear. So input divided by output. So these are our 3 ratios that we use. Now I'm notorious for flipping things. So I would make these, pop these in a list so I have them to refer to really quickly when you're doing calculations. Because even when I do up the slides, I have to keep going back and double checking because that's one of my weaknesses is I flip numbers around. You'll notice the number of teeth, it's driver divided by driven. Speed is driven divided by driver. They flip. Why do they flip? Well, small gears move small. The reason for the flip, we're going to find that, I put that on the next slide. We'll look at it on the next slide. It always helps when I print things off and look at what's coming next, okay? So we'll look at why these 2 ratios flip, the speed and the torque. But I want to think about here, why would torque and speed be used for actual mechanical advantage and teeth used for ideal? Well, is torque affected by friction? Definitely, because it includes force. Is speed affected by friction? Well, if gears slip, does that change the speed that they turn? Definitely. The number of teeth on a gear, is that going to change if there's friction or no friction? No, that number stays the same unless a tooth breaks. So that's why torque and speed get used for the actual mechanical advantage, and the ideal mechanical advantage is always calculated using the tooth ratio. Just a couple of slides left and we finish off here. So applying mechanical advantage. Why is the driver-driven gear position flipped in the mechanical advantage ratios? So I'm thinking about torque and speed. Well, if we look here, the big gear, we've already said, this has a large torque, and this one has small torque. Why? Because it's the same amount of force that's being applied a shorter distance from the axle, from the center. But what about speed? Well, let's just think for a second. Let's say this gear turns once. Will this gear turn more than once or less than once? Well, the small gear is going to turn a bunch of times because it's got less teeth per turn. And I didn't actually do a count on how many teeth, but if there's 10 teeth here, which I think there's maybe more like 15 teeth, but if there was 10 teeth here and 5 teeth here, for every 1 turn the big gear makes, the little one's going to make 2. So the little gear is going to be faster, and this one's going to be slower. So if we look at the ratio, large torque goes with small speed. So the driver gear has my large torque. In order to get the same ratio, because it has a small speed, I have to actually put it on the bottom. My driven gear, when we look at torque, it has the small torque. So it goes on the bottom. So big number divided by little number. Over here, the small gear has the fast speed. So in order to get big number divided by little number again, we have to flip their positions. And if we flipped which gear was driving which, I guess I said the big gear was driving the little gear. If we actually do it the way it's supposed to, the little gear driving the big gear, we would have high speed divided by low speed. So when we do, so that's going to give us a bigger mechanical advantage. If we use torque, we're going to have to do large torque divided by small torque in order to get the same numbers. Okay? So that's why they flip. It's because they have opposite relationships. The more torque you have, the less speed. You'll see here, more torque, less speed, less torque, more speed. That's why we have to gear up and down in our vehicle. All right, so I want you just to kind of stop, think, and apply for a minute. First of all, I want to think about what happens if the mechanical advantage is more than one. What advantage do we get? So let's look at our gears and we're going to figure out which one has a mechanical advantage that's more than one. Well, in order to figure that out, let's look at our formulas. If we want this number to be bigger than 1, well, the top or the bottom have to be larger. The top number has to be larger. So we're going to have a larger numerator in the mechanical advantage ratio. Okay, so if we look, the driver gear has to have more teeth than the driven gear. So which one of these three is that scenario? The driver gear has more teeth than the driven gear. Well, that would mean our input gear, which is here, has more teeth than the output gear. So this one has a mechanical advantage that is greater than 1. Okay, this one, the teeth are the same, so this would give us a ratio of 1. And over here, mechanical advantage, the driver gear is small, the driven gear is really large, so this one is going to have a mechanical advantage of less than 1. So let's look at this. What's the advantage of this ratio? So we'll call this A and we'll line this up with A. What's the advantage of A? Well, let's look at what happens to each of these formulas if the numerator is bigger. So if we look here, the mechanical advantage using speed, if the numerator is bigger, the driven gear is moving faster. So that means the output gear is moving faster than what I put in. That's a speed advantage. Let's look at torque. It says the torque on the driver gear is the largest. So is there a torque advantage? No, because the torque is going to be less on the output gear. So this one has less torque, but more speed. So what's the advantage when you have a mechanical advantage more than one? It's a speed advantage. Okay. Now let's look at scenario B. If the mechanical advantage is less than 1, so that's this scenario, what's the advantage? Well, let's do the same thing. Let's compare what happens to speed and what happens to torque, and it'll tell us whether we have a speed advantage or a torque advantage. So if we look here, the input gear, what do we know has to happen here? So for B, we have to have a larger denominator. So what I like to do in each of our ratios. So what I like to do is I look here and I look, okay, speed. The driver gear, the gear that's driving, has to be the largest. So I look and see, well, what got bigger? So in this case, this is the fast one. This is slow. Is it a speed advantage? No, we're not gaining any speed. So what are we gaining? Well, let's look at torque. The bottom number has to be the largest. The denominator has to be largest. The torque on the driven gear, so we're gaining torque because it has to be larger than the torque on the driver gear. So hopefully that makes sense. I paused and recorded and re-recorded that because it just wasn't coming out right. So hopefully the two mesh together okay. But that's what we kind of look at, is look at what happens and what's the advantage for each of the scenarios. And then we can apply that in some real world stuff. So I'm going to do just a couple math questions. Hopefully take these three formulas with you. We may have to pop back to them. We're just going to do a couple of calculations. I only have really two calculation examples. So the first thing I'm going to make a note of is my gear ratio, my mechanical advantage. It's the same as a gear ratio. And it's teeth, driver, or in by the teeth out. I like to write that down just so I have it, and then I look back, and speed is opposite. Is equal to driven over driver. And then torque happens to match the teeth. So you'll see teeth and torque are the same, and speed is the one that's flipped. Okay, so first of all, calculate the gear ratio when a 20-tooth input gear drives a 10-tooth output gear. So input is the driver, and this is my driven. So mechanical advantage is going to be putting them in 20 over 100, which is 0.2, and there's never any units on mechanical advantage. Easy math. If 50 foot-pounds of torque are applied to the driving gear, how much torque is provided at the axle of the output gear, assuming 100% efficiency? So 100% efficiency means the mechanical advantage with teeth is going to be the same as the mechanical advantage with torque. The mechanical advantage isn't changing. So that means my mechanical advantage stays at 0.2. So what's the formula for mechanical advantage using torque? So it's going to be torque of the driver, or torque in, divided by torque out. So 0.2 is equal to the torque on the driver gear was 50 over X. And if it's foot-pounds that we put in, we get foot-pounds out. Now, this is one of those ones I would recommend putting a 1 underneath and doing cross multiplication and division. 1 times 50 is 50. 0.2 times X equals 0.2X, and then divide by 0.2. Cancels. X equals 50 divided by 0.2. We get 250 foot-pounds. Does that make sense? Well, I've got a bigger diameter, bigger radius on the output gear, so the torque should increase. That makes sense. And then the very last one says if the input gear is running at 300 RPMs, how many RPMs will the output gear run? First of all, it's going to be bigger or small. Well, you can look at your picture. The arrow here is moving faster than the arrow here. So we know it's going to be a slower gear. The big gear is going to move slower. Mechanical advantage with speed has to be the same. So we're going to use this formula. So we get our speed for the driven gear. So our speed out divided by speed in. Mechanical 0.2 has to be equal to the speed of the output gear is what I want to know. So I'm going to have X over 300. 1 times X is X. 0.2 times 300 gives me 60 RPM. So it moves slower. So again, we're back to first semester gear ratios. Pretty simple. Last but not least, one quick question. What's the gear ratio of a set of gears where the driving gear has 72 teeth and the driven gear has 18 teeth? Just go back to your gear ratio and solve. So we know that the gear ratio is the driver gear divided by the driven gear. So mechanical advantage is going to be the driver gear, 72 teeth, divided by 18, which gives us a mechanical advantage of 4. So it's going to have 4 times less torque, but we're going to find on the output gear, because the big gear is turning the little one, but we're going to find it has 4 times more speed applied. If this was the gear ratio on a bike, would it make it easier to climb a hill or to gain more speed? So Remember it asked what would happen if. So this one I think maybe easiest to sketch a picture. So 72T, the big gear, driving a small gear. So this is my in and this is my out. Climbing a hill, I need force, which is torque. So looking at this, if the gear ratio is 4, for this gear set, that means it has this kind of a setup. Input gear is bigger than the output gear. Will it be easier to climb the hill or to gain more speed? Well, let's look. Larger distance means the input gear has more torque. The output gear has less torque. So am I gaining more torque? Am I gaining more pushing power? No. What's happening to the little gear though? The little gear is faster. So I'm getting faster output, so it's going to be easier to gain speed. I'll get speed, but I won't get more climbing ability. So, you know, sometimes we say we gear down to climb a hill. We gear down. What it means is we're getting a smaller mechanical advantage. The mechanical advantage number is going down, which increases my torque, but it reduces my speed. Last but not least, gears versus belt and pulley. Belt and pulley are exactly the same as gears, and I really don't spend a huge amount of time with them because it's the same math. You use exactly the same formulas, except instead of using teeth for the size of the gear, you would use your diameter. So in this type of belt and pulley, they're both, the advantage is both of them are going to move in, you know how gears move in opposite directions. With a belt, everything moves in the same direction. We can still change speed because the small one's going to move faster than the big one. We can still change torque because the turning force applied to the axle is going to change depending on the distance the belt is from the axle. So it's exactly the same kind of thing. So we don't need to really do new math, but I do want you to think about what are some pros and cons. So we'll just talk about a couple of pros and cons. Belts require friction to stay in place. If a belt isn't tight and holding with friction to the pulley, if it's slipping, is it going to transfer the work 100%? No. So one of the cons of a belt and pulley is when slipping happens, they're less efficient. With gears, does slipping happen very often? No, not nearly as much. So gears can stand a lot more force. So that's why we use them in motors where they need a lot of force. Now, if you just have a fan belt and there's not as much force on it, we can get away with a belt and pulley system. The belt and pulley systems are typically more prone to slipping. And when they're slipping, they're more prone, they're often less efficient. So that's one of the biggest things. Gears are much less likely to slip. Wind turbines, they use gears, they don't use any belt and pulleys. But now for HVAC and for fans, they'll often use belt and pulley. Why? Well, they're just smaller, they don't have as much force on them, so we don't have to worry about slip as much. So there's advantages and disadvantages. Gears turn in opposite directions, so we're always going to change your direction. When you have two gears together, belt and pulley are in the same direction. You can have two pulleys separated by a long distance in a long belt. But gears, you might have to have a whole bunch of gears in the middle. So there's some advantages and disadvantages to the two systems just from a logistics perspective, but the math on them is exactly the same. And that finishes up our section on gears.